Hello everyone, today we'll study functions. First of all, let me introduce what is a function. For a function, we can always think of a machine. Think of a machine called F. Machine F looks like this. Assume this is machine F. For machine F, we input something called X. Then the machine gives something out called Y. Think of this machine. We put something into the machine and then we get something out. If for every input there exists exactly one output, if for every input there exists exactly one output, then we say this machine is a function. Then we say this machine F is a function. If for every input there's exactly one output, then we say this machine is a function. Otherwise, it's not a function. If I input something and we get nothing out, it's not a function. If I input something, we get nothing out, it's not a function. If I input something, I get two items, it's also not a function. In the above machine diagram, we write f of x equal to y. This is read f of x. We write f of x equal to y, where f is a function. X is the input, f is a function. What's in the parentheses is the input. And y is the output. In this machine diagram here, I input x and get y out. So I write f of x equal to y. X is the input, f is the function, x is the input, and y is the output. In general, there are many representations of functions. Here, let me show you some function representations. First of all, a function can be represented using arrow diagram. A function sometimes can be represented using an arrow diagram. A function sometimes can be represented using an arrow diagram. For example, consider this arrow diagram. There are two sets. One set contains numbers 1, 2, 3, 4. Another set contains numbers 1, 2, and 3. The arrow looks like this. The arrow goes from 1 to 2. The arrow goes from 1 to 2. The arrow goes from 2 to 1. The arrow goes from 3 to 2. The arrow goes from 4 to 3. Does this arrow diagram represent a function? Let's check. Assume the function goes this way from left to right. If I input 1, the output is 2. If I input 2, the output is 1. If I input 3, the output is 2. If I input 4, the output is 3. Since for every input there's exactly one output, this is a function. Since for every input there's exactly one output, this is a function. So we can consider this as a function f. If I input 1, I get 2. So I say f of 1 equal to 2. If I input 2, I get 1. So I say f of 2 equal to 1. If I input 3, I get 2. So I say f of 3 equal to 2. If I input 4, I get 3. So I say f of 4 equal to 3. This is an example of arrow diagram. Also, a function can be represented using a table of values. A function can be represented using a table of values. A function can be represented using a table of values. A function sometimes can be represented using a table of values. For example, consider a table of two rows. Consider a table of two rows. First row is x, second row is y. In general, for a table of values, we consider the upper row as input, lower row as output. In general, for a table of values, we consider the upper row as inputs, and lower row as outputs. In general, for a table of values, we consider the upper row as inputs, and we consider the lower row as outputs. So for this table value here, when the input is 2, output is 7. When the input is 4, output is -1. When the input is 6, output is 3. When the input is 8, the output is -2. When the input is 10, output is 6. When the input is 12, output is -8. So for table of values, we consider the upper row as input, lower row as output. Since here, for every input, there exists exactly one output, this is a function. Since here, for every input, there exists exactly one output, so this is a function. This function says f of 2 equal to 7. When the input is 2, output is 7. F of 4 equal to -1. When the input is 4, output is -1. F of 6 is 3. When the input is 6, output is 3. F of 8 is -2. When the input is 8, output is -2. f of 10 is 6. When the input is 10, output is 6. F of 12 is negative a. When the input is 12, output is negative a. Next, let me introduce functions represented by graphs. A function can sometimes be represented by graphs in the xy plane. A function can be represented using a graph in the xy plane. Let me show you an example. Consider this graph in the xy plane. Consider this graph in the xy plane. 0, 1, 2, 3, negative 1, negative 2, negative 3, 1, 2, 3, 4, 5, 6. Consider this graph. Usually we consider the value in the x-axis as input, the value in the y-axis as output. For example, if the input is 0, the output is 1. If the input is 1, the output is 2. If the input is 2, the output is 5. If the input is negative 1, the output is 1. If the input is negative 2, the output is 5, and so on. So here we can see that for every input, there's exactly one output. For every input, there's exactly one output. So this graph represents a function. In this graph, we can see that if I input 0, I get 1. F of 0 equal to 1. If I input 1, the output is 2. If I input 2, the output is 5. If I input negative 1, the output is 2. If I input negative 2, output is 5. So that's a function represented by using a graph. Next, let me introduce functions represented by equations. A function can sometimes be represented by an equation with only x and y. A function can be represented by an equation. A function can be represented using an equation with only x and y. Using an equation with only x and y, with variables x and y. For example, 2x plus 3y equal to 6. In this equation, we consider x as input, y as output. In the equation of x and y, we consider x as an input. We consider y as an output. For example, if the input is 0, I can plug in 0 for x and then solve for y. I have 2 times 0 plus 3y equal to 6. 2 times 0 is 0. 0 plus 3y is 3y. If I divide both sides by 3, I get y equal to 2. So when the input is 0, output is 2. Also, if the input is 1, I can plug in 1 for x and then solve for y. I get 2 times 1 plus 3y equal to 6. 2 times 1 is 2. 2 plus 3y equal to 6. Here I can subtract 2 from both sides. So I get 3y equal to 4. And then I can divide both sides by 3. I get y equal to 4 over 3. So when the input is 1, output is 4 over 3. So here we can see that for every input, there's exactly one output. So this equation represents a function. For every input, there's exactly one output. So this equation represents a function. For this equation, we know that f of 0 is 2. If I input 0, the output is 2. If I input 1, output is 4 over 3. So f of 1 equal to 4 over 3. Same thing works for other numbers. So here we can see that a function can be represented using an arrow diagram, a table of values, a graph in the xy plane, or equation of x and y. However, we need to be very careful. A function can be represented using arrow diagram, but not every arrow diagram represents a function. A function can be represented by an arrow diagram. However, not every arrow diagram represents a function. Similarly, a function can be represented by using a table of values. However, not every table of values represents a function. A function can be represented by a graph in the xy plane. However, not every graph in the xy plane represents a function. And similarly, a function can be represented by an equation. However, not every equation represents a function. Next, I'll show you some examples. For each of the following arrow diagrams, determine whether it represents a function. In the first arrow diagram, it points 1 to 4, 2 to 5, 3 to 6, and 4 to 6. Does it represent a function? Since for every input, there's exactly one output, yes, this is a function. Since for every input, there's exactly one output. When the input is 1, output is 4. When the input is 2, output is 5. When the input is 3, output is 6. When the input is 4, output is 6. Since for every input, there's exactly one output, yes, this represents a function. Second diagram, it points 7 to 4 and 7 to 5. It points 8 to 6 and 9 to 7. Does it represent a function? Here, when the input is 7, there are two outputs, 4 and 5. So this arrow diagram doesn't represent a function. No, it doesn't represent a function. It doesn't represent a function. Because when the input is 7, there are two outputs, 4 and 5. so it doesn't represent a function. When the input is 7, there are 2 outputs. If for any input there are 2 outputs, this is not a function. So this arrow diagram doesn't represent a function. Next diagram, it points -1 to 1, -1 to 2. It points -2 to 3, -3 to 1, and -4 to 3. Does it represent a function? Here, when the input is -1, there are 2 outputs. Output is 1 and 2. When the input is -1, there are 2 outputs. If for any input there are 2 outputs, this is not a function. So no, it doesn't represent a function. It doesn't represent a function. Because when the input is -1, there are 2 outputs, 1 and 2. Because when the input is -1, there are 2 outputs, 1 and 2. -1 point to 1, it points -1 to 1 and -1 to 2. When the input is -1, there are 2 outputs. So this diagram doesn't represent a function. Next, does this diagram represent a function? It points -1 to 1, 0 to 1, 1 to 1. It points everything to 1. Does this represent a function? Here, when the input is -1, output is 1. When the input is 0, output is 1. When the input is 1, output is 1. Since for every input, there's exactly 1 output, yes, this represents a function. Yes, it represents a function. When the input is -1, there's only 1 output, which is 1. When the input is 0, there's only 1 output, which is also 1. When the input is 1, there's only 1 output, which is 1. The output could be the same, but for every input, if there's only 1 output, this is a function. Next example, for each of the following tables of values, determine whether it represents a function. So, for a table of values, usually the first row represents input, second row represents output. Here, in the first table, when the input is 0, output is -1. When the input is 1, output is -4. When the input is 2, output is 1. When the input is 3, output is 2. Here, for every input, there's exactly 1 output. So yes, this is a function. It represents a function. Second table here. First row always represents input. Second row always represents output. Here, when the input is 3, output is 1. When the input is 4, output is 2. When the input is 5, output is 2. When the input is 6, output is 3. So for every input, there's exactly 1 output. So yes, it represents a function. The output could be the same. When we input 4 and 5, output could be the same. But for every input, there's exactly 1 output. Yes, it represents a function. The output could be the same. When the input is 4, there's only 1 output, which is 2. When the input is 5, output is 2. Output could be the same. Next example. In a table, first row always represents input. Second row always represents output. When the input is 1, output is 4. When the input is 2, output is -3. When the input is 2, output is 6. When the input is 3, output is 9. Does it represent a function? Here, be very, very careful. When the input is 2, there are 2 outputs. When the input is 2, there are 2 outputs. When the input is 2, output could be either 3 or 6. So it doesn't represent a function. Because when the input is 2, the output is -3 and 6. Because when the input is 2, the output is -3 and 6. If for some input there is more than one output, this is not a function. This table doesn't represent a function. Next example, for any table, the first row always represents the input, second row always represents the output. Here, when the input is 7, output is -4. When the input is A, output is -1. When the input is 9, output is 2. When the input is A, output is 3. Does this table represent a function? Be very, very careful. When the input is A, there are 2 outputs. Output could be either -1 or 3. So this table doesn't represent a function. When the input is A, there are 2 outputs. Output is -1 and 3. So it doesn't represent a function. No, it doesn't represent a function. Because when the input is A, when the input is A, there are 2 outputs, -1 and 3. When the input is A, the outputs are -1 and 3. Since for some input, there is more than one output, this is not a function. This table doesn't represent a function. Next example, for each of the following graphs in the xy plane, determine whether it represents a function. In general, if we try to tell whether a graph represents a function, it's not straightforward and it's not easy. So in order to tell whether a graph represents a function, we use vertical line test. Vertical line test will tell us whether a graph represents a function. Vertical line test says, if every vertical line crosses the graph no more than once, then this graph represents a function. If every vertical line crosses the graph no more than once, then this graph represents a function. If there's a vertical line that crosses the graph more than once, if there's a vertical line that crosses the graph more than once, then this graph doesn't represent a function. For example, if there's a vertical line that crosses the graph more than once, then this graph doesn't represent a function. So for example, in this graph, suppose there's a 1 here, there's a 1 here, and this vertical line, it crosses the curve twice. And this vertical line here, it crosses the curve twice. Assume this value here is -2 and +2. What does it tell us? This vertical line tells us when x is 1, there are 2 y values. In general, x represents input, y represents output. So when the input is 1, there are 2 outputs. So this graph doesn't represent a function. So vertical line test says, if every vertical line crosses the graph no more than once, then the graph represents a function. If there's a vertical line crossing the graph more than once, then this graph doesn't represent a function. If every vertical line crosses the graph no more than once, That means for every x, there's only one y. For every x, there's only one y. So it represents a function. If there's a vertical line that crosses the curve more than once, then that means for this x value, there are multiple y values. For this input, there are multiple outputs. So this graph doesn't represent a function. So this graph, it doesn't represent a function. Because there's a vertical line that crosses the curve more than once. Because there's a vertical line that crosses the curve more than once. Now, first graph. Does this graph represent a function? Let's try vertical line test. Here we can see that every vertical line crosses the curve exactly once. Every vertical line crosses the curve exactly once. So yes, it represents a function. That means for every x, there's exactly one y. For every input, there's exactly one output. So yes, it represents a function. Does this graph represent a function? Let's try vertical line test. We can see that every vertical line crosses the curve exactly once. Every vertical line crosses the curve exactly once. So yes, it represents a function. That means for every x, there's exactly one y. For every input, there's exactly one output. So yes, it represents a function. Example 3, how about this graph? Let's try vertical line test. For this vertical line here, we can see that it crossed the curve more than once. For this vertical line here, we can see that it crossed the curve more than once. If there's a vertical line that crosses the curve more than once, that means for this input here, for this x here, there are two corresponding y values. That means for this input here, there are two outputs. So this graph doesn't represent a function. It doesn't represent a function. Because there's a vertical line that crosses the curve more than once. Because there's a vertical line that crosses the curve more than once. Number 5. Does this graph represent a function? Let's try vertical line test. For this part here, the vertical line test is okay. Vertical line crosses the curve exactly once. How about this part here? How about this vertical line? How about this vertical line? Here we can see that for this vertical line, they're all okay. Only this vertical line at -2. For vertical line at -2, it crossed the curve infinitely many times. And this piece here, this vertical line crossed the curve infinitely many times. So when s is -2, y could be 2, 3, 4, 5, 6, 7, 8, 9. So this doesn't pass vertical line test. If a vertical line cross the curve, touch the curve more than once, this is not a function. So it doesn't represent a function. Because when s is -2, the vertical line touch the graph more than once. When s is -2, the vertical line touch the graph more than once. This doesn't represent a graph because when s is -2, this vertical line touch the graph more than once. Next graph, does it represent a function? Let's try vertical line test. Here we can see that every vertical line crosses the curve exactly once. Every vertical line crosses the graph exactly once. So yes, it represents a function. It represents a function. Since every vertical line crosses the curve exactly once. So for graphs, we use vertical line test in general. If every vertical line crosses the graph exactly once, then the graph represents a function. But if there's a vertical line that crosses the graph more than once, then this graph doesn't represent a function. That's called a vertical line test. Next example, for each of the following equations, determine whether it represents y as a function of x. First example, 4x plus 3y equals 12. How can we tell whether this equation represents y as a function of x? So here you can try to solve an equation for y first. If I try to solve this equation for y, I can subtract 4x from both sides. So I get 3y equal to -4x plus 12. Next, I can divide both sides by 3. If I divide both sides by 3, I get y equal to -4/3x plus 4. If we can isolate y, that means for every x, I can find a y value. For every x value, I can find a y value. So this expression is a function of x. So yes, it represents a function of x. It represents y as a function of x. Since for every x, we can find corresponding y. This equation represents a function of x. Next example, y plus s squared equal to 4. Does this equation represent y as a function of x? So let's try to solve this equation for y. For this equation, I can subtract x squared from both sides. If I subtract x squared from both sides, I get y equal to 4 minus s squared. If we are able to isolate y, that means for every x value, there's corresponding y. So this equation represents y as a function of x. Since I can isolate y, that means for every x, there's exactly one y value. Then this equation represents y as a function of x. Yes, it represents y as a function of x. In general, if an equation represents y as a function of x, this equation can be written as a function. Here we can write f of x equal to -4/3x plus 4. If this equation represents y as a function of x, we can write y equal to f of x equal to negative 4 over 3x plus 4. And similarly for this equation, y equal to 4 minus x squared, since this is a function, it can be written as f of x equal to 4 minus x squared. Since this is a function, I can write it as f of x equal to 4 minus x squared. Next example, x squared plus y squared equal to 4. Does this equation represent y as a function of x? So let's try to get y by itself. For this equation, I can subtract x squared from both sides first. If I subtract x squared from both sides, I get y squared equal to 4 minus x squared. How can we isolate y here? If we try to get y by itself, we must take square root on both sides. And be very, very careful. If I take square root on both sides, I need to add plus or minus sign. Be very, very careful. For example, if we have x squared equal to 4, when I take square root, I need to add plus or minus. So s equal to plus or minus 2. That means positive 2 squared is 4. Negative 2 squared is also 4. So when we take square root, we need to always add plus or minus sign in the front. So here, when we take square root on both sides, we need to add plus or minus sign in the front. So if I isolate y, here I get y equal to plus or minus square root of 4 minus x squared. Does this represent a function? Let's try plugging some numbers. For example, if I let s equal to 0, what do I get for y? If I let s equal to 0, I have y equal to square plus or minus square root of 4 minus 0 squared. 4 minus 0 squared is 4. Square root of 4 is 2. So when s equal to 0, y equal to plus or minus 2. When s equal to 0, y equal to plus or minus 2. If for some x, y has 2 outputs. If for some x, y has 2 values, then this equation doesn't represent a function of x. So no, it doesn't represent a function of x. It doesn't represent y as a function of x. Because when s equal to 0, y equal to plus minus 2. If for some input there are 2 outputs, this is not a function. Because when s equal to 0, y equal to plus minus 2. If for some input there are 2 outputs, this equation doesn't represent a function. Next example, 2 times absolute value of x plus y equal to a. Does this equation represent y as a function of x? Let's try to isolate y. Here I can subtract 2 times absolute value of x on both sides, which means y equal to a minus 2 times absolute value of x. Since here I get y by itself, and for every x here, there's exactly one y value. For every x I input, I get exactly one y value. So this is a function of x. This represents y as a function of x. So yes, it represents y as a function of x. So in order to determine whether an equation represents y as a function of x, we should look at y by itself first. if there's only one solution for y, that means for every x, there's exactly one y value. Then this equation represents y as a function of x. However, if there are two solutions for y, if we solve for y, there are two solutions for y, for example, plus or minus. If there are two solutions for y, that means for some x value, there are two corresponding y values. That means for some x value, there are two corresponding y values. If for some x value, there are two y values, this equation doesn't represent y as a function of x. If for some x, there are two y values, then this equation doesn't represent y as a function of x. Next example. Absolute value of x plus y equal to 3. We try to determine whether it represents y as a function of x. So let's try to solve an equation for y first. How do we solve this equation here? Absolute value of x plus y is equal to 3. If an absolute value of x plus y equal to 3, that means what's inside? That means what's inside must be either plus or minus 3. If absolute value of x plus y equal to 3, that means what's inside must be either positive 3 or negative 3. That means x plus y is either positive 3 or negative 3. Then in both cases, we try to get y by itself. In the first case, I can subtract x from both sides. So I get y equal to negative x plus 3. In the second equation, I can also subtract x from both sides. I get y equal to negative x minus 3. So here we can see that we have two solutions for y. Here we have two solutions for y. That means if I let x equal to 0, then y equal to positive 3 and negative 3. If I let x equal to 0, y equal to positive 3 or negative 3. That means for some x value, there are two y values. So it doesn't represent a function of y. It doesn't represent y as a function of x. It doesn't represent y as a function of x. Because when x equal to 0, y equal to plus or minus 3. If for some x value there exists two y values, this equation doesn't represent y as a function of x. Next, x squared plus y cubed equal to 1. Determine whether this equation represents y as a function of x. So let's try to isolate y first. Try to get y by itself first. Here I can subtract x squared from both sides first. If I subtract x squared from both sides, I get y cubed equal to 1 minus x squared. In order to get y by itself, I take cube root on both sides. When I take cube root, I don't add plus minus sign. In general, when we take even number of roots, second root, fourth root, sixth root, we must add plus minus sign. When we take odd number of roots, like cube root, fifth root, or the seventh root, we don't add plus minus sign. When we take even number of roots, we must add plus minus sign. When we take odd number of roots, we don't add plus minus sign. So here, when I take cube root, I don't add plus minus sign. I get y equal to cube root of 1 minus x squared. Since there's only one solution for y, that means for every x, there exists only one corresponding y. Since there's only one solution for y, that means for every x, there exists only one corresponding y. So this is a function. This equation represents y as a function of x. So yes, it represents y as a function of x. If there's only one solution for y, that means for every x, there exists exactly one y. Then it represents y as a function of x. If this equation represents y as a function of x, usually we can write it as f of x equal to cube root of 1 minus x squared. And same thing for number 4. If this equation represents y as a function of x, usually we can write it as f of x equal to a minus 2 absolute value of x, assuming y equal to f of x. Next, y equal to 1. Does this equation represent a function? So for y equal to 1, let's test some s values. If s is 0, y is 1. If s is 1, y is 1. If s is 2, y is 1. That means for every x, y is 1. So yes, this represents a function, represent y as a function of x. Since for every x, there exists exactly one y. Since for every x, there exists exactly one y. So yes, this equation represents a function of x. It represents y as a function of x. Since for every x, there exists exactly one y. Y is always 1. If this equation represents a function, we can write it as f of x equal to 1. Assuming f of x equal to y, we can write it as f of x equal to 1. Next, does this equation x equal to 2 represent y as a function of x? Let's test some numbers. X equal to 2, that means for every y, x is always 2. Y equal to 1 means for every x, y is always 1. X equal to 2 means for every x, for every y, x is always 2. For every y, x is always 2. So when y is 0, x is 2. When y is 1, x is 2. When y is 2, x is 2. Remember here, x represents input. For function, x represents input, y represents output. When the input is 2, there are more than one output. When the input is 2, there are more than one output. So this equation doesn't represent a function. So no, it doesn't represent a function. It doesn't represent y as a function of x. Because when s is 2, there exists more than one y values. Sorry, that's a mistake. It doesn't represent y as a function of x. It doesn't represent y as a function of x. Because when x equal to 2, there exists more than one y values. So keep in mind that the equation y equal to some number always represent y as a function of x. And the equation s equal to some number doesn't represent y as a function of x, because there's no y here. It doesn't represent y as a function of x. Next, let me introduce domain and range of a function. Let y equal to f of x be a function. The domain of function f denoted by D sub f, is the set of all real numbers which are valid to plug into the function. And the range of function f, denoted by R sub f, is the set of all possible outputs that function f has. In order to understand domain and range better, let me show you an example. Consider this function f of x equal to square root of x plus 2 plus 1. If I graph this function using a graphing calculator, that's what I get in my calculator. If I graph this function in my calculator, that's what I get here. In my calculator, I get some graph looks like this. That's what I get in my graphing calculator. What's the domain of this function? Domain represents the set of real numbers which are ready to plug into the function. If I plug in -2, I get 1. If I plug in -2 for x, -2 plus 2 is 0. Square root of 0 is 0. 0 plus 1 is 1. If I plug in -1, I get some number here. If I plug in 0, I get a number here. If I plug in 1, I get a number here. If I plug in 2, I get 3. So the number we are allowed to plug in is a number greater than -2. How about -3? If I plug in, what do I get? If I plug in -3, -3 plus 2 is -1. Square root of -1 is undefined. If I plug in -4, -4 plus 2 is -2. Square root of -2 is also undefined. So we are not allowed to plug in the numbers below -2. So the numbers which are ready to plug in is the numbers greater or equal to -2. That's the domain of function f. The number greater than -2 is the interval from -2 to infinity. The number greater or equal to -2 is the interval from -2 to infinity. That's the domain of function f. Now, how about range of function f? Range of function f represents the set of all possible outputs that function f has. The set of all possible outputs that function f has. If I plug in -2, I get 1. If I plug in -1, I get something more than 1. If I plug in 0, I also get something more than 1. If I plug in 1, I get something more than 1. If I plug in 2, I get something more than 2. So the range is the set of real numbers from 1 to infinity, which is the interval from 1 to infinity. That's the range. Range is the set of all possible outputs that function f has. Here we can see that all outputs are greater than 1. So the range is the set of real numbers from 1 to infinity, which is the interval from 1 to infinity including 1. That's the domain and range. In general, finding domain is easier. Finding range is not straightforward. Finding range is not straightforward unless we sketch a graph. In general, finding range is not easy. Finding domain is easier. Next, let me show you how to find domains for some functions. Find a domain for each of the following functions. First example, f of x equal to x squared plus x plus 5. We know that the domain of a function is the set of all real numbers which are valid to plug into the function. So far, for plug-in, the only restriction is that the denominator cannot be 0. And what's under the square root cannot be negative. What's under the square root must be greater or equal to 0. That's the only restriction for plug-in. What's under the square root cannot be 0. What's under the denominator cannot be 0. What's under the square root must be greater than or equal to 0. If the square root is on the denominator, then it must be strictly greater than 0. Since it must be greater than or equal to 0, it cannot be 0. So for the square root on the denominator, it must be strictly greater than 0. So that's the only restriction for plug-in. In the first example here, for a domain, if there's no denominator, no square root, that means every number is ready to plug in. So domain is the set of all real numbers. The set of all real numbers in the number line is the numbers from negative infinity to infinity. The set of all real numbers on the number line is the interval from negative infinity to infinity. Since every number is ready to plug in, it's a set of real number from negative infinity to infinity. That's the domain of function f. Next example, g of x equal to 5x minus 6. G of x equal to 5x minus 6. So far, for domain, the only restriction is that the denominator cannot be 0. What's under the square root must be greater than or equal to 0. If the square root is on the denominator, then what's under the square root must be strictly greater than 0. In this problem, in this function, if there's no denominator, there's no square root, then domain is always the set of all real numbers. So domain of function g is the interval from negative infinity to infinity. Then represent a set of all real numbers. Next example. Function h of x equal to square root of 2x plus 4. Function h of x equal to square root of 2x plus 4. If there's a square root, we know that what's under the square root must be greater than or equal to 0. What's under the square root must be greater than or equal to 0. So for domain, we need to make 2x plus 4 greater than or equal to 0. And then solve this inequality for x. The way to solve inequality is the same as solving equations. We try to get s by itself on the left side. So I can first of all subtract 4 from both sides. I get 2x is greater or equal to negative 4. Then I can divide both sides by 2. If I divide both sides by 2, I get s is greater or equal to negative 2. If s is greater or equal to negative 2, in the number line it looks like this. Number line is from negative infinity to infinity. Negative 2 is somewhere on the number line. Since negative 2 is included, we draw a solid circle. Since negative 2 is included, draw a solid circle. X is greater than negative 2. Numbers to the right side are greater than negative 2. So it's the region to the right side. Then represent the interval from negative 2 to infinity, including negative 2. That's domain of function h. That's domain of function h. D sub h represents domain of function h. Next example. K of x equal to 3 over x minus 1. So far, for domain, the only restriction is that the denominator cannot be 0. What's under square root must be greater or equal to 0. And if square root is on the denominator, then it must be strictly greater than 0. In this problem, what we have is x minus 1 on the denominator. So for the domain, we know that since the denominator cannot be 0, that means x minus 1 cannot be 0. If x minus 1 cannot be 0, I can add 1 to both sides. I can add 1 to both sides. That means x cannot equal to 1. If x doesn't equal to 1, that means in the number line, x could be any real number except 1. Could be any real number except 1. If I remove number 1 from number line, I draw open circle here for number 1. If I remove 1 point from a line, I cut it into 2 pieces. If I remove 1 point from a line, I cut it into 2 pieces. First piece is from negative infinity to 1, not including 1. Second piece is from 1 to infinity, not including 1. If there are 2 intervals, we put union in the middle to connect two intervals. Put union in the middle. That's the domain of function h. D sub h represents domain of function, this is function k. D sub k represents domain of function k. That's the domain of function k. Next example. F of x equal to 4 over square root of x plus 3. Find domain of function f. For square root on the denominator, what's under square root must be strictly greater than 0. So x plus 3 must be strictly greater than 0. What's under square root on the denominator must be strictly greater than 0. So here, x plus 3 must be strictly greater than 0. Then try to get s by itself. Here I can subtract 3 from both sides. I get s is greater than negative 3. If I draw a number line from net infinity to infinity, there's a number line from net infinity to infinity. Negative 3 is somewhere on the number line. There's negative 3 somewhere on the number line. Since it's not included, I draw open circle. Since negative 3 is not included, draw open circle. We have x is greater than negative 3. We know that number to the right side of negative 3 is greater than negative 3. So it's to the region to the right side of negative 3. That's the interval from negative 3 to infinity. Negative 3 is not included. This is domain of function f. This is domain of function f. Next. G of x equal to square root of x minus 2 over x minus 6. Number 6. G of x equal to square root of x minus 2 over x minus 6. So for domain, keep two things in mind. What's under square root must be greater than or equal to 0. What's under square root must be greater or equal to 0. And what's on the denominator cannot be 0. What's on the denominator cannot be 0. So what we have here is x minus 2 must be greater than or equal to 0. That's what's under square root. And the denominator, x minus 6, cannot be 0. What's under square root must be greater than or equal to 0. And what's on the denominator cannot be 0. They'll need to solve both inequalities. For the first inequality, I can add 2 to both sides. If I add 2 to both sides, what I get is x greater or equal to 2. If I solve the second inequality, I can add 6 to both sides. If I add 6 to both sides, I get x not equal to 6. So what we have is x is greater than or equal to 2, and x cannot be 6. X is greater than or equal to 2, and x cannot be 6. Let's draw a number line. Number 2 is somewhere in the number line here. Since number 2 is included, draw a solid circle. We know that number to the right side of 2 is greater than 2. Number to the right side of 2 is greater than 2. So that's from 2 to infinity. Also, we need to consider that s cannot be 6. We need to consider s cannot be 6. If I remove 6 from the line, I draw open circle. If I remove 6 from the line, that means number 6 is not included. I draw open circle as 6. If I remove 1 point from a line, I cut it into 2 pieces. If I remove 1 point from the line, I cut it into 2 pieces. Here the first piece is from 2 to 6, including 2, but not including 6. Second piece is from 6 to infinity, not including 6. If there are 2 intervals, put union in the middle to connect 2 intervals. That's the domain of function g. Next. Function h of x equal to 2x over s squared minus 4. Function h of x equal to 2x over s squared minus 4. So for domain, the only restriction is that what's on the denominator cannot be 0. What's under square root must be greater or equal to 0. If the square root is on the denominator, then what's under square root must be strictly greater than 0. Here what we have is the denominator, s squared minus 4. So what's on the denominator cannot be 0. If s squared minus 4 cannot be 0, I can add 4 to both sides. That means s squared cannot equal to 4. If s squared doesn't equal to 4, I can take square root on both sides. Remember, when I take square root, I need to add plus or minus sign. Square root of 4 is 2. So s doesn't equal to plus or minus 2. Since s squared cannot be 4, s cannot be plus or minus 2. So s can be all real numbers except plus or minus 2. Let's draw a number line. So the domain is the set of all real numbers except plus or minus 2. If I remove positive 2 and negative 2, then they are not included. Draw open circle for positive 2 and negative 2. If I remove positive 2 and negative 2 from the number line, they are not included. So draw open circle for positive 2, for both positive 2 and negative 2. If I remove 2 points from a number line, I cut it into 3 pieces. If I remove 2 points from a line, I cut it into 3 pieces. So first piece is from negative infinity to negative 2. Negative 2 is not included. Second piece is from negative 2 to 2. Both negative 2 and 2 they are not included. Third piece is from 2 to infinity. 2 is not included. If there are multiple intervals, we put union in the middle to connect the intervals. That's the domain of function h. That's the domain of function h. Next, k of x equal to cube root of 1 minus 2x. For cube root, what's under the root could be either positive or negative. It doesn't matter what's under square root, what's under the cube root. So if there's no denominator, no square root, the domain is always a set all real numbers. If there's no denominator, no square root. If there's no denominator, no square root, the domain is always a set of all real numbers. So all real number means entire number line from negative infinity to infinity. That's all real numbers. So the domain of function k is the interval from negative infinity to infinity. Next, let me show you how to evaluate a function with the given values. First example, let f of x equal to 2x plus 3. Evaluate f of 2, f of 6, f of negative 4, and f of negative 1. How to evaluate f of 2? When we try to evaluate f of 2, we plug in 2 for each x. We plug 2 into the function for x. Here 2 represents x. I plug in 2 for x in the function. So here I get 2 times 2 plus 3. I plug in 2 for x. This number 2 here represents x in the parentheses. So I plug in 2 for x. I get 2 times 2 plus 3. 2 times 2 is 4. 4 plus 3 is 7. So f of 2 equal to 7. F of 2 equal to 7. Next, how about f of 6? For f of 6, number 6 represents x. For f of 6, number 6 represents x. So we plug in 6 for x in the function. Plug in 6 for x in the function. I get 2 times 6 plus 3. 2 times 6 is 12. 12 plus 3 is 15. Next, how about f of negative 4? For f of negative 4 represents x. So we plug in negative 4 for x. 2 times negative 4 is negative 8. negative 8 plus 3 is negative 5. So f of negative 4 equal to negative 5. How about f of negative 1? For f of negative 1 represents x. So we plug in negative 1 for x. We get 2 times negative 1 plus 3. 2 times negative 1 is negative 2. Negative 2 plus 3 is positive 1. So f of negative 1 equal to positive 1. Next example. Let g of x equal to 4 minus x squared plus 3x evaluate g of 2, g of negative 1, g of negative 5, and g of 3. So let's find g of 2 first. For g of 2, we plug in 2 for each x in the function. Here, number 2 represents x. We plug in 2 for each x in the function. I get 4 minus 2 squared plus 3 times 2. Do the exponent first. 2 squared is 4. 3 times 2 is 6. 4 minus 4 is 0. 0 plus 6 is 6. So we say g of 2 equal to 6. How about g of negative 1? For g of negative 1, we plug in negative 1 for x. Here, negative 1 represents x. We plug in negative 1 for x. We get 4 minus negative 1 squared plus 3 times negative 1. Do the exponent first. Negative 1 squared is positive 1. Negative 1 times negative 1 is positive 1. Then, last term here, positive 3 times negative 1. Positive 3 times negative 1 is negative 3. 4 minus 1 is 3. 3 minus 3 is 0. That means g of negative 1 equal to 0. Next, find g of negative 5. For g of negative 5, we plug in negative 5 for each x. Here, negative 5 represents x. We plug in negative 5 for x. I get 4 minus negative 5 squared plus 3 times negative 5. Negative 5 squared is positive 25. Double negative is positive. Negative 5 squared is positive 25. Next, positive 3 times negative 5 is negative 15. Then 4 minus 25 is negative 21. Negative 21 minus 15. Consider we are combining like terms. They have the same sign, keep the sign and the magnitude. 21 plus 15 is 36. So g of negative 5 is negative 36. Next, find g of 3. For g of 3, we plug in 3 for each x. Number 3 here represents x. So I get 4 minus 3 squared plus 3 times 3. Plug in number 3 for each x. I get 4 minus 3 squared is 9 plus 3 times 3 is 9. Positive 9 and negative 9 can cancel. Answer is 4. That means g of 3 equal to 4. Next example, let h of x equal to x over s plus 2. Evaluate h of 2, h of negative 4, h of negative 7, and h of 3. So, for h of 2, we plug in 2 for each x. Number 2 represents x. We plug in 2 for each x, which is 2 over 2 plus 2. In the denominator, 2 plus 2 is 4. And 2 over 4 can be reduced as 1 over 2. So h of 2 equal to 1 over 2. How about h of negative 4? For h of negative 4, we plug in negative 4 for each x. That's negative 4 over negative 4 plus 2. If we do the denominator first, on the denominator, negative 4 plus 2 is negative 2. And then negative 4 divided by negative 2 is positive 2, which means h of negative 4 equal to 2. Next, how about h of negative 7? For h of negative 7, we plug in negative 7 for each x. I get negative 7 over negative 7 plus 2. Numerator stays the same. On the denominator, negative 7 plus 2 is negative 5. Double negative is positive, but 7 divided by 4 is not divisible. We leave it the way it is. Negative number divided by negative number, double negative is positive, but 7 divided by 4 is not divisible. I leave it the way it is. So the answer is 7 over 5. h of negative 7 equal to 7 over 5. How about h of 3? For h of 3, we plug in 3 for each x. I get 3 over 3 plus 2. Numerator stays the same. On the denominator, 3 plus 2 is 5. And 3 and 5, 3 divided by 5 is not divisible. I leave it the way it is. That means h of 3 equal to 3 over 5. Next example. Let k of x equal to square root of x squared plus 1. Evaluate k of 1, k of 3, k of negative 2, and k of negative 5. Let's evaluate k of 1 first. For k of 1, number 1 represents x, so we plug in 1 for each x in the function. I get 1 squared plus 1. 1 squared is 1. 1 plus 1 is 2. Square root of 2 cannot be reduced, so we leave it the way it is. So k of 1 equal to square root of 2. Next, how about k of 3? For k of 3, we plug in 3 for x. I get square root of 3 squared plus 1. 3 squared is 9. 9 plus 1 is 10. So I get square root of 10, which means k of 3 equal to square root of 10. Next, how about k of negative 2? For k of negative 2, we plug in negative 2 for x. That's square root of negative 2 squared plus 1. Negative 2 squared is positive 4. 4 plus 1 is 5. So k of negative 2 equal to square root of 5. Next, k of negative 5. For k of negative 5, we plug in negative 5 for each x. So I get square root of negative 5 squared plus 1. Negative 5 squared is positive 25. 25 plus 1 is 26. So I get square root of 26, which means k of negative 5 equal to square root of 26. Next example. Let f of x equal to s squared plus 1 if s is greater or equal to 1, and f of x equal to 2x if x is less than 1. Evaluate f of 5, f of 1, f of negative 1, and f of negative 6. Here, a function in its form is called a piecewise defined function. A function in its form is called a piecewise defined function. Then how to evaluate f of 5? For f of 5, this number 5 here represents x. Let's check here. Is 5 greater than 1 or 5 less than 1? Since number 5 is greater than 1, we apply in the first piece of the function. Since 5 represents x and number 5 is greater than 1, we apply in the first piece of the function. I plug in 5 into the first piece for x. I get 5 squared plus 1. 5 squared is 25. 25 plus 1 is 26. So f of 5 is 26. Now, how about f of 1? For f of 1, this number 1 here represents x. Let's check the condition first. Is number 1 greater or equal to 1, or 1 is less than 1? Here, 1 equal to 1, so it satisfies the first condition. I plug in 1 into the first piece of the function. Since 1 satisfies the first condition, I plug in 1 into the first piece of the function. If I plug in 1 here, I get 1 squared plus 1. 1 squared is 1. 1 plus 1 is 2. So f of 1 equal to 2. Now, next. How about f of negative 1? For f of negative 1 represents x. Let's check the condition. Is negative 1 greater than 1, or negative 1 is less than 1? It's clear that negative 1 is less than 1. Since negative 1 satisfies the second condition, we plug in negative 1 into the second piece of the function. Since negative 1 satisfies the condition of the second piece of the function, we plug in negative 1 into the second piece of the function. I get 2 times negative 1. 2 times negative 1 is negative 2, which means f of negative 1 equal to negative 2. Next, how about f of negative 6? Negative 6 represents x here. Let's check the conditions. Is negative 6 greater than 1, or negative 6 is less than 1? We know that negative 6 is less than 1. Since negative 6 satisfies the second condition, we plug in negative 6 into the second piece of the function. I get 2 times negative 6. 2 times negative 6 is negative 12. So here, f of negative 6 equal to negative 12. That's how we evaluate a piecewise defined function. Next example. G of x equal to 2x plus 3 if x is less than 2, and equal to 1 minus x if x is between 2 and 6 including 2, and equal to 3x plus 1 if x is greater than or equal to 6. Evaluate g of 10, g of 6, g of 3, g of 2, g of 1, and g of negative 3. This is also a piecewise defined function. Let's evaluate each of them. How to evaluate g of 10? For g of 10, number 10 represents x. Which condition does 10 satisfy? Here, 10 is greater than 6. 10 is greater than 6. So it satisfies the third condition. We apply the third piece of the function. Since it satisfies the third condition, we apply the third piece of the function. I get 3 times 10 plus 1. Plugging 10 into the third piece of the function, I get 3 times 10 plus 1. 3 times 10 is 30. 30 plus 1 is 31. Next, how about g of 6? For g of 6, we try to check this 6 represents x. This 6 represents x. We try to check condition. Which condition does number 6 satisfy? Which condition does number 6 satisfy? Is 6 less than 2? Is 6 between 2 and 6? Is 6 greater or equal to 6? Here, number 6 is equal to 6. So it satisfies the third condition. If we satisfy the third condition, we plug in 6 into the third piece of the function. I get 3 times 6 plus 1. 3 times 6 is 18. 18 plus 1 is 19. So g of 6 is 19. Next, evaluate g of 3. For g of 3, number 3 here represents x. Number 3 represents x. Let's try to check. Which condition here does number 3 satisfy? Does 3 less than 2? Is 3 between 2 and 6? Is 3 greater than 6? Here you can see that 3 is between 2 and 6. So it satisfies the second condition. Number 3 satisfies the second condition. So I plug in 3 into the second piece of the function. I get 1 minus 3. 1 minus 3 is negative 2. That means g of 3 equal to negative 2. Next, how about g of 2? For g of 2, number 2 represents x. So let's check condition for number 2 first. Which condition does number 2 satisfy here? Since number 2 equal to 2, it satisfies the second condition. Since number 2 here equal to 2, it satisfies the second condition. So I plug in 2 into the second piece of the function. I get 1 minus 2. And we know that 1 minus 2 is negative 1. That means g of 2 equal to negative 1. Next, how about g of 1? For g of 1, number 1 represents x. Let's check the conditions. Which condition does number 1 satisfy? Is 1 less than 2? Is 1 between 2 and 6? Or is 1 greater than 6? Here we know that 1 is less than 2. So number 1 satisfies the first condition. We plug in number 1 into the first piece of the function. Here I get 2 times 1 plus 3. 2 times 1 is 2. And 2 plus 3 is 5. Which means g of 1 equal to 5. Last one. How about g of negative 3? For g of negative 3 represents x. Let's check conditions here. Which condition does negative 3 satisfy? Here we can see that negative 3 is less than 2. So negative 3 satisfies the first condition. I plug in negative 3 into the first piece of the function. So plug negative 3 into the first piece of the function. I get 2 times negative 3 plus 3. 2 times negative 3 is negative 6. Negative 6 plus 3 is negative 3. Which means g of negative 3 equal to negative 3. So that's how we evaluate a piecewise defined function. Next example. Let f of x equal to 4x minus 3. Evaluate f of 7, f of negative 9, f of letter t, f of negative x, f of s plus 1, f of 2x plus 3, f of s squared minus 4, and f of s squared minus 2x plus 5. So let's start from f of 7. How to evaluate f of 7? For f of 7, number 7 represents x. We plug in 7 for each x, which means I replace x with 7. I get 4 times 7 minus 3. Here, 4 times 7 is 28. 28 minus 3 is 25. Next, how about f of negative 9? For f of negative 9 represents x. So I plug in negative 9 for x, which means I replace x with negative 9. I get 4 times negative 9 minus 3. Here, 4 times negative 9 is negative 36. Negative 36 minus 3 is negative 39. So f of negative 9 equal to negative 39. Next, How about f of t? For f of t, t represents x. So I plug in t for x, which means I replace x with what's in the parentheses. Replace x with what's in the parentheses. I get 4t minus 3. Replace x with what's in the parentheses. I get 4t minus 3. And 4t minus 3 cannot be simplified. So that's the answer. F of t equal to 4t minus 3. That's the answer. Next, how about f of negative x? For f of negative x, we plug in negative x for x, which means I replace this x with what's in the parentheses. I get 4 times negative x minus 3. I replace x with what's in the parentheses. I get 4 times negative x minus 3. If I simplify here, positive 4 times negative x is negative 4x. And negative 4x minus 3, they cannot be combined. They are non-like terms. They cannot be combined. That's the answer. F of negative x equal to negative 4x minus 3. Next, how about f of x plus 1? How about f of x plus 1? For f of x plus 1, I replace this x with what's in the parentheses. Replace this x with what's in the parentheses. I get 4 times x plus 1 minus 3. That's the first step. Replace x with what's in the parentheses. And then simplify this expression. I can first of all distribute 4. If I distribute 4, I get 4x plus 4 minus 3. Then combine like terms. Positive 4 and negative 3 in like terms. 4 minus 3 is 1. I get 4x plus 1. So f of x plus 1 equal to 4x plus 1. Next, f of 2x plus 3. What's f of 2x plus 3? For f of 2x plus 3, I replace x with what's in the parentheses. I replace x with what's in the parentheses. I get 4 times 2x plus 3 minus 3. If I distribute 4, I get ax plus 12 minus 3. Then I can combine like terms. 12 and number 3 they are like terms. If I combine like terms, 12 minus 3 is 9. So I get ax plus 9, which means f of 2x plus 3 is ax plus 9. Next, how about f of s squared minus 4? For f of s squared minus 4, I replace x with what's in the parentheses. I get 4 times s squared minus 4 minus 3. That's the first step. Replace x with what's in the parentheses. Then distribute 4. I get 4s squared minus 16 minus 3. If I try to combine like terms here, we know that negative 16 and negative 3 they are like terms. If I combine like terms, negative 16 plus negative 3 they have the same sign. Keep the sign and the magnitude. 16 plus 3 is 19. So I get 4s squared minus 19, which means f of s squared minus 4 equal to 4s squared minus 19. Next, f of s squared minus 2x plus 5. For f of s squared minus 2x plus 5, first step, replace x with what's in the parentheses. Replace x with what's in the parentheses. I get 4 times s squared minus 2x plus 5 minus 3. That's the first step. Replace x with what's in the parentheses. And then I can distribute and simplify. If I distribute 4, I get 4s squared minus ax plus 20 minus 3. Here I can combine like terms. 20 and 3 they are like terms. 20 minus 3 is 17. So I get 4s squared minus ax plus 17, which means f of s squared minus 2x plus 5 equal to 4s squared minus ax plus 17. Next example, let g of x equal to s squared minus x. Evaluate g of 4, g of negative a, g of 2x, g of x squared, g of x plus 1, and g of 2 minus x. Let's start from the first one. How to evaluate g of 4? For g of 4, we replace x with number 4. I get 4 squared minus 4. Replace x with number 4. That's the first step. Then simplify. 4 squared is 16. 16 minus 4 is 12, which means g of 4 equal to 12. Next, how about g of negative a? For g of negative a, we replace x with what's in the parentheses. Always replace each x with what's in the parentheses. So I get negative a squared minus negative a. Plug in negative a for each x. I get negative a squared minus negative a. Negative a squared is positive 64. And minus negative a, double negative is positive. We get 64 plus a, which is 72. Which means g of negative a equal to 72. Next, how about g of 2x? For g of 2x, we replace each x with what's in the parentheses. So I get 2x squared minus 2x. That's the first step. Replace each x with what's in the parentheses. I get 2x squared minus 2x. And then simplify. 2x squared, I distribute square to each of them. 2 squared is 4. S squared is s squared minus 2x. And 4x squared minus 2x, they are non-like terms. They cannot be combined. That's the final answer. So g of 2x equal to 4x squared minus 2x. Next, how about g of s squared? For g of s squared, first step, replace each x with s squared. Replace each x with what's in the parentheses. I get s squared squared minus s squared. Replace each x with what's in the parentheses. I get s squared squared minus s squared. Then simplify. S squared squared, 2 times 2 is 4. I get x raised to power 4 minus s squared. And they are non-like terms. They cannot be combined. We leave an answer the way it is. That's the answer. G of s squared equal to s to the power 4 minus s squared. Next one. How about g of s plus 1? How about g of s plus 1? For g of s plus 1, go to function g. Replace each x with what's in the parentheses. Replace each x with what's in the parentheses. Here we get x plus 1 squared minus s plus 1. Replace each x with what's in the parentheses. I get s plus 1 squared minus s plus 1. Then simplify. How do we simplify s plus 1 squared? S plus 1 squared, it means s plus 1 times s plus 1. If I distribute, I get x squared plus x plus x plus 1. Then I combine like terms. X plus x is 2x. I get s squared plus 2x plus 1. So x plus 1 squared equal to s squared plus 2x plus 1. Minus x plus 1. Here I can distribute negative sign. If I distribute negative sign, positive x becomes negative x. Positive 1 becomes negative 1. Then I can combine like terms. S squared stays the same. Positive 2x minus 1x is positive 1x. Positive 1 minus 1, they get cancelled. So the answer is s squared plus x. G of s plus 1 equal to s squared plus x. That's an answer. Next one. How do we evaluate g of 2 minus x? For g of 2 minus x, First step, go to function g. Replace each x with what's in the parentheses. So here I get 2 minus x squared minus 2 minus x. First step, replace each x with what's in the parentheses. I get 2 minus x squared minus 2 minus x. Let's evaluate the perfect square first. What's 2 minus x squared? 2 minus x squared, it means 2 minus x times 2 minus x. If we distribute, we get 4 minus 2x minus 2x plus x squared. If we combine like terms, I can combine negative 2x and negative 2x. Negative 2x plus negative 2x is negative 4x. X squared stays the same. So if I expand the perfect square, I get 4 minus 4x plus x squared. For the second part, we get negative minus 2 plus x minus 2 minus x. Here I can distribute negative sign. Consider this as a negative sign. Distribute negative sign. Positive 2 becomes negative 2. And negative x, double negative is positive, it becomes positive x. Next, we combine like terms. When we combine like terms, run the term with higher power first. X squared stays the same. Negative 4x and positive 1x, they are like terms. If I combine like terms, negative 4 plus 1 is negative 3. I get negative 3x. Number 4 and negative 2, they are like terms. 4 minus 2 is positive 2. So the answer is x squared minus 3x plus 2. G of 2 minus x equal to x squared minus 3x plus 2. Next, let me show you how to graph functions. Graph each of the following functions. First example, f of x equal to x squared. How do we graph this function? When we try to graph a function, we treat y equal to f of x. Then make a table for x and y, and then sketch the graph by plotting points. So first of all, make a table for x and y. Y equal to f of x, which is x squared. Then pick some value for x. Pick some value for x. In order to graph a function, we must pick value for x. We cannot pick value for y. We must pick value for x. So pick some value for x. Some positive, some in general, pick some positive value and some negative value. Here I can pick negative 2, negative 1, 0, and 1, and 2. Then for each x, find y. Here, y equal to f of x, which is x squared. If I plug in negative 2 squared is positive 4. If I plug in negative 1 squared is positive 1. If I plug in 0 squared is 0. If I plug in 1 squared is 1. If I plug in 2 squared is 4. Then sketch the graph by plotting points. That's the x-axis. That's the y-axis. Plot the points. First point, negative 2, 4. When x is negative 2, y is 4. Second point, negative 1, 1. When x is negative 1, y is 1. Next point, 0, 0. When x is 0, y is 0. Next point, 1, 1. When x is 1, y is 1. Next point, 2, 4. When x is 2, y is 4. Then connect the points using smooth curves. Connect the points using smooth curves. That's the graph of this function. Next example. G of x equal to half of x plus 1. G of x equal to half of x plus 1. So, in order to sketch graph for this function, I treat y equal to g of x. And then make table for x and y. We treat y equal to g of x. If y equal to g of x, y equal to half of x plus 1. And then make table for x and y. We pick some value here for x. Here we can pick some positive value and negative value for x. When we try to graph a function, we can only pick values for x. We cannot pick values for y. If we pick value for y, it will be very, very complicated. So when we try to graph a function by plotting points, we can only pick values for x. Let's pick some positive value and negative value for x. In general, we pick -2, -1, 0, 1, and 2. Then plug in each number into function here. Find y value. If I plug in -2, what do I get? I get half times -2 plus 1. Half times -2 is -1. -1 plus 1 is 0. If I plug in -1 here, what do I get? If I plug in -1, I get half times -1 plus 1. Half times -1 is -half. -half plus 1 is +half. -half plus 1 is +half. If I plug in 0, what do I get? If I plug in 0, I get half times 0 plus 1. Half times 0 is 0. 0 plus 1 is 1. If I plug in 0, I get 1. If I plug in 1, what do I get? If I plug in 1, I get half times 1 plus 1. Half times 1 is half. Half plus 1 is 1.5. 1.5 is 3/2. So if I plug in 1, I get 3/2. If I plug in 2, what do I get? If I plug in 2, half times 2 is 1. 1 plus 1 is 2. I get 2. If I plug in 2, I get 2. Next, we can sketch the graph by plotting points. Assume that's the x-axis, that's the y-axis. When s is -2, y is 0. That's the first point. Second point, when s is -1, y is half. When s is -1, y is half, somewhere here. Next point, when s is 0, y is 1. Point is here. Next, when s is 1, y is 3/2. 3/2 is 1.5. So when s is 1, y is 1.5 is here. Next, when s is 2, y is 2. 2, 2 is here. Then connect all these points. We have a straight line. That's the graph of the function y equal to g of x. In the first one, that's the graph of the function y equal to f of x. Next, how do we graph a piecewise defined function? F of x equal to s squared minus 3x if x is less or equal to 2, and function equal to 6 minus x if s is greater than 2. How do we graph this piecewise defined function? So for a piecewise defined function, we must make table for each piece. Make table for each piece. let's make a table for the first piece, x. Assume y equal to f of x. For the first piece, f of x equal to x squared minus 3x. For the first piece, x must be less or equal to 3. Sorry, x must be less or equal to 2. So start from 2. Pick some smaller values. Since x is less than 2, pick some smaller values. Here I can pick 1 and 0. Those are numbers less or equal to 2. Usually we pick 3 points for each piece. If I plug in 2, what do I get? I get 2 squared minus 3 times 2. 2 squared is 4. 3 times 2 is 6. 4 minus 6 is negative 2. So if I plug in 2, I get negative 2. Or if I plug in 1, if I plug in 1 for x, I have 1 squared minus 3 times 1. 3 times 1 is 3. 1 minus 3 is negative 2. So if I plug in 1, I also get negative 2. Or if I plug in 0, I get 0 squared minus 3 times 0. 0 squared is 0. 3 times 0 is also 0. 0 minus 0 is 0. So if I plug in 0, I get 0. That's what I get from the first piece. Next, do the same thing to the second piece. Make table for the second piece of the function. Assume y equal to f of x. So for the second piece, f of x equal to 6 minus x. Second piece says x must be greater than 2. So start from 2. Pick some numbers that's greater than 2. For numbers greater than 2, we can pick 3 and 4. Of course, the more point we pick, the more accurate the graph is. In general, pick 3 points. Sometimes we can pick more. Then plug in each x. If I plug in 2 for x, 6 minus 2 is 4. If I plug in 3 for x, 6 minus 3 is 3. If I plug in 4 for x, 6 minus 4 is 2. Next, let's try to sketch a graph based on these two tables. That's an x-axis. And that's the y-axis. Then plot points. For the first piece, first point is 2, comma negative 2. When x is 2, y is negative 2 is here. And number 2 is included in the first piece. It's a solid point. Number 2 is included in the first piece of the function. So when x is 2, we have a solid point. When x is 1, we get negative 2. When x is 1, y is negative 2. When x is 0, y is 0. Then connect these 3 points using smooth curves. Connect these 3 points using smooth curve. Connect these 3 points using smooth curve. The curve must be smooth. Connect these 3 points using smooth curve. That's the first piece. Second piece. When x is 2, y is 4. In the second piece, number 2 is not included. In the second piece, number 2 is not included. So I draw open circle from the point 2, 4. Since number 2 is not included, we draw open circle from the point 2, 4. That's the first point. Second point, 3, 3. Where x is 3, y is 3. It's here. That's the starting point. Only the end point is not included. Only number 2 is not included. Next point, when x is 4, y is 2. When x is 2, when x is 4, y is 2. That's the third point. Then connect these points. That's a straight line. That's the second piece. That's the first piece, that's the second piece. Altogether, this is the graph of this piecewise defined function. Next example, g of x equal to -1 if x is less than 0. G of x equal to s squared minus 4 if x is between 0 and 3, including 0. And g of x equal to 2x minus 1 if x is greater than or equal to 3. Graph this function. So this is a piecewise defined function. It has 3 pieces. We make table for each piece individually. First piece, make table for x and y. We assume y equal to g of x. And when x is less than 0, first piece, when x is less than 0, g of x equal to -1. So when x is less than 0, start from 0, pick 3 numbers that's less than 0. Start from 0, pick 3 numbers that's less than 0. I can pick 0, -1, and -2. And then here, when x is 0, y is -1. When x is -1, y is -1. When x is -2, y is also -1. This y doesn't depend on x. It doesn't matter what x is, y is always -1. So that's the table for the first piece of the function. Next, make table for the second piece of the function. For the second piece of the function, g of x equal to s squared minus 4. So y equal to s squared minus 4, since y equal to g of x. Then choose some value for x. Here x is between 0 and 3. So if x is between 0 and 3, x could be 0, 1, 2, 3. Here we must pick all points. Since x is between 0 and 3, pick all points. Then plug in each x into the function. If I plug in 0, I get 0 squared minus 4. 0 squared minus 4. 0 squared is 0. 0 minus 4 is -4. If I plug in 0, I get -4. If I plug in 1 for x, I get 1 squared minus 4. 1 squared is 1. 1 minus 4 is -3. So if I plug in 1, I get -3. Or if I plug in 2, I get 2 squared minus 4. We know that 2 squared is 4. 4 minus 4 is 0. If I plug in 2, I get 0. If I plug in 3 for x, I get 3 squared minus 4. 3 squared is 9. 9 minus 4 is 5. So when x is 3, y is 5. Next, let's make table for the third piece. For the third piece, y equal to g of x, which is 2x minus 1. For the third piece, y equal to 2x minus 1. Then, here, for the third piece, x is greater or equal to 3. So we start from 3. For the third piece, x is greater or equal to 3, start from 3. pick some numbers greater than 3. Here we can pick 4 and 5. Usually pick 3 numbers greater or equal to 3. Then we plug in each x into the function to find y. If I plug in 3 for x, I get 2 times 3 minus 1. 2 times 3 is 6. 6 minus 1 is 5. So when x is 3, y is 5. If I plug in 4 for x, I get 2 times 4 minus 1. 2 times 4 is 8. 8 minus 1 is 7. So when x is 4, y is 7. Next, plug in 5 for x. I get 2 times 5 minus 1. 2 times 5 is 10. 10 minus 1 is 9. Which means when x is 5, y is 9. When x is 5, y is 9. Next, plot its points and sketch the graph. That's the y-axis, and that's the x-axis. Then plot the points. In the first table, first point is 0, comma, negative 1. 0, comma, negative 1 is here. And in the first piece of the function, 0 is not included. X equal to 0 is not included. So it's an open circle for this point. It's an open circle for this point. 0, comma, negative 1. Since 0 is not included, it's an open circle for this point. Second point, negative 1, comma, negative 1. That's a solid point. Next point, negative 2, comma, negative 1. That's a solid point. Then connect these points. For the first piece, x is less than 0. Number to the left side are less than 0. So only draw arrow to the left side, not on the right side. Right side terminates here. Right side terminates at 0. On the left side, draw arrow on the left side. X is less than 0, means x could be negative 3, negative 4, negative 5, and so on. So draw arrow to the left side, not on the right side. Right side terminates at 0 here. Second piece. First point is 0, comma, negative 4. When x is 0, y is negative 4. It's here. It's here. 0, comma, negative 4 is here. And for the second point, 0 is included. So it's a solid point here. So it's a solid point at 0, comma, negative 4. Since in the second piece, 0 is included. So it's a solid point at negative 4. Next point, 1, comma, negative 3. When x is 1, y is negative 3. 1, comma, negative 3 is here. Next point, 2, comma, 0. When x is 2, y is 0. It's here. Next point, 3, comma, 5. When x is 3, y is 5. When x is 3, y is 5. 1, 2, 3, 4, 5 is here. Then connect all these points using smooth curves. Connect all these points using smooth curves. And for the last point here, 3 is not included. This is an open circle. For the last point, 3, comma, 5. Since 3 is not included, that's an open circle. Then connect these points using smooth curves. Connect these points using smooth curves. That's the second piece. Now the third piece. First point, 3, 5. In the third piece, 3 is included. So that's a solid point at 3, 5. 3, 5 is a solid point here. So this solid point will fill out the hole here. This solid point at 3, 5, it will fill out this hole here. That's the first point, 3, 5. It fills out this hole here. Second point is 4, 7. Or X is 4, Y is 7. Third point, 5, 9. Or X is 5, Y is 9. Then connect these 3 points. And draw arrow to the right side. The left side terminates at this point. So draw arrow on the right side. That's the graph of this piecewise defined function. That's the graph. Y equal to g of x. In the previous problem, we said y equal to f of x. So in the previous problem, these two pieces together is the graph y equal to f of x. In this problem, all three pieces together is the graph y equal to g of x. Next, let me introduce two formulas. F of x plus h minus f of x over h, and f of x minus f of a over s minus a. They are both called the difference quotient. Next, let's look at some simple examples. Let f of x equal to 3x plus 1. Find the difference quotients. F of 1 plus h minus f of 1. Over h, and f of x minus f of 1 over s minus 1, assuming the denominator is not 0, assuming h is not 0, assuming x is not 1, assuming the denominator is not 0. Find the difference quotient. So let's do the first one first. How do we evaluate f of 1 plus h minus f of 1 over h? For f of 1 plus h, we first of all plotting 1 plus h for x. First of all, plotting 1 plus h for x. I get 3 times 1 plus h plus 1. So here, for f of 1 plus h, I plug in 1 plus h for each x. Second part, minus f of 1. For f of 1, we plug in 1 for x. I get 3 times 1 plus 1. Denominator stays the same. So here, for f of 1 plus h, we plug in 1 plus h for x. I get 3 times 1 plus h plus 1 minus f of 1. For f of 1, I plug in 1 for x. I get 3 times 1 plus 1. And then simplify. In the numerator here, I can distribute 3. If I distribute 3, I get 3 plus 3h plus 1. That's the first bracket. In the second bracket, 3 times 1 is 3 plus 1. over h. And then combine like terms. In the parentheses, 3 plus 1 is 4. So I get 3h plus 4. In the second parentheses, 3 plus 1 is also 4. Then in the numerator, plus 4 and minus 4 cancel. What's left is 3h. 3h over h. I can cancel h from top to the bottom. I get 3. So the first difference quotient equal to 3. The first difference quotient equal to 3. Next, how to evaluate the second difference quotient? How to evaluate f of x minus f of 1 over s minus 1? How to evaluate f of x minus f of 1 over s minus 1? So here, for f of x minus f of 1 over s minus 1, do the numerator first. In the numerator, f of x is a function itself. F of x is 3x plus 1. F of x is the function itself. 3x plus 1. Minus f of 1. What's f of 1 here? For f of 1, we plug in 1 for x. I get 3 times 1 plus 1. For f of 1, we plug in 1 for x. We get 3 times 1 plus 1 over s minus 1. Let's simplify the second bracket first. In the first bracket, 3x plus 1 stays the same. In the second bracket here, 3 times 1 is 4. Sorry, 3 times 1 is 3. 3 plus 1 is 4. Then if I combine like terms, I get 3x. 1 plus negative 4 is negative 3. Then simplify. On the numerator, I can factor power number 3. If I power number 3, what's left is x minus 1. If I factor power number 3, what's left is x minus 1 over x minus 1. Then we can cancel x minus 1 from top to the bottom. What's left is number 3. So that's an answer to the second difference quotient. In general, we don't get the same answer. That's a coincidence. In general, we don't get the same answer. That's a coincidence. Next example. Let f of x equal to x squared plus 4. Find the difference quotient. F of 2 plus h minus f of 2 over h, and another difference quotient, f of x minus f of 2 over s minus 2. Let's look at the first difference quotient first. F of 2 plus h minus f of 2 over h. For this expression, we first of all plug in 2 plus h for x. We first of all plug in 2 plus h for x. If I plug in 2 plus h for x, I get 2 plus h squared plus 4. That's what we have for the first function. For the second function, we have f of 2. That means we plug in 2 for x. Plug in 2 for x. We have 2 squared plus 4. If I plug in 2 for x, we have 2 squared plus 4 over h. Then simplify. In the first bracket, let's expand the perfect square first. What's 2 plus h squared? 2 plus h squared, that can be written as 2 plus h times 2 plus h. If I distribute, I get 4 plus 2h plus 2h plus h squared. Combine like terms. 2h plus 2h is 4h plus h squared. That's the perfect square. 2 plus h squared. So I get 4 plus 4h plus h squared plus 4. That's what we have here in the first parenthesis. In the second parenthesis, 2 squared is 4. 4 plus 4. Let's leave it for now. 2 squared is 4. We have 4 plus 4. Denominator is h. If we simplify, in the first parenthesis, 4 plus 4 is a. So I get a plus 4h plus h squared minus, in the second parenthesis, 4 plus 4 is also a over h. Then a minus a can cancel. We get 4h plus h squared over h. Next, in the numerator, I can factor h out. In the numerator, I can pull out h. If I pull out h, what's left is 4 plus h. If I pull out h, what's left is 4 plus another h. Then I can cancel h from top and bottom. What's left is 4 plus h. That's an answer to the first difference quotient. Next, let's solve the other one. For the other difference quotient, we have f of x minus f of 2 over x minus 2. Here, f of x is x squared plus 4. How about f of 2? For f of 2, we plug in 2 for x. That's 2 squared minus 4 over s minus 2. Then simplify. In the first parenthesis, s squared plus 4 stays the same. In the second parenthesis, 2 squared is 4. 4 plus 4 is a. In the denominator, we have s minus 2. It stays the same. Then in the numerator, combine like terms. S squared stays the same. 4 minus a is negative 4 over x minus 2. Then how do we simplify this? In the numerator, s squared minus 4, it can be factored. They are difference of perfect squares. S squared and 4, they are both perfect squares. That's called a difference of perfect square. We put x on each parenthesis. Number 4 is 2 times 2. 2 squared is 4. So I can put 2 on each parenthesis. Operation is always 1 plus, 1 minus. So s squared minus 4 can be factored as s plus 2 times s minus 2. That's called a difference of perfect squares. That's a numerator. Denominator stays the same. Now here, x minus 2 on the top and the bottom get cancelled completely. What's left is s plus 2. That's an answer to the second difference quotient.